Hello, my name is Andrew Morris and I'm Head of Pharmacy at Swansea University. This is tutorial 3A, where we're going to look at predicting expiry dates, particularly around rates and orders of reactions. If you've not listened to the earlier tutorials, I suggest you go and listen to those before continuing with this. So in tutorial 1 we looked at the expiry date of medicines, and we saw how that expiry date gives us a date after which the medicine shouldn't be used. There are various reasons why that might be, but one of those is the fact that over time the concentration of the drug or the active ingredient can slowly decline, and eventually we'll get to the point where it's not suitable for the patient to carry on taking this. And we ask the question, okay, how can we actually go about determining what the expiry date of a medicine should be? So we'll think about that more now in a little bit of detail. So when a medicine has been developed, possibly a new medicine, in order to work out what that expiry date should be, the company which has developed the medicine will leave the medicine, they'll store it over a long period of time, basically under what we call sort of in-use conditions. So for example, if the medicine is meant to be stored at room temperature, it will be left somewhere at room temperature. If it needs to be stored away from light, it might be put somewhere else, in a drawer for example, away from a light source. Some medicines need to be refrigerated. Some medicines even need to be stored in a freezer. So all of this is specific to a medicine, and most medicines which you would receive from a pharmacy are typically stored at room temperature. But the key thing is here is that stability testing of the medicine should take place under those in-use storage conditions. Now, that does create a little bit of a problem, because we can leave the medicine on the shelf for 1 year, 2 years, 3 years, and we can keep going back and analysing that medicine, and we can see how much drug is left. And eventually we might get to a point where the level of the drug has fallen below the manufacturer or the regulator's specification. So for example, there might be only 95% of the drug left, or 90% of the drug left. So at that point we'll say, okay, we've determined that's what the expiry date should be. But the problem for that is the pharmaceutical company which has developed the medicine would have to wait all of these years before they could then actually sell the medicine, and that means that patients would miss out on possibly a new medicine that would really help them in whatever condition they have. And it also means, of course, that the company isn't able to sell that medicine, so they're not making any money for that. So there are lots of reasons why we might want to try and speed up that process by which we work out what the expiry date is. So one of the processes that we use is something called an accelerated stability test. So accelerated stability testing can be used to speed up that process. And with regards to that, essentially what we would do is increase one of the factors which we know breaks down or helps break down the particular medicine. So it's possible that the temperature of storage could be increased. Maybe light sources increased, possibly humidity, and also pH. Now in this tutorial we're just going to consider one of these. We're going to look at heat, and the reason we're going to consider that is because there's something called the Arrhenius Equation, and that enables us to make predictions of stability at one temperature based upon experimental data at another temperature. So for example, we could predict the stability of a drug in solution at room temperature based upon experimental data at a higher temperature. And as you would expect, if you increase the temperature, you will increase the rate of drug breakdown. So you'll be able to find out your estimated expiry date much more sooner. So let's think now about accelerated stability testing. And let's think about the drug we've looked at in the earlier tutorials. That's the drug aspirin, which, as you know by now, reacts with water and breaks down to salicylic acid and ethanoic acid. So how can we firstly calculate the rate of aspirin hydrolysis? And we've explored different mechanisms of actually quantifying breakdown of a drug in the earlier tutorials. So in this scenario, we're assuming that we've got a liquid aspirin formulation, a simple formulation, just aspirin dissolved in water. So the rate of aspirin hydrolysis varies with temperature. So it's important that we maintain that variable. We don't want the temperature to change. So the easiest way of doing this in a lab is just to use what's called a water bath. Very simple piece of apparatus. Just you can see here in the picture, you've got a metal container containing just simple water, and that's heated up and it would be held at a particular temperature. You can see the dial on the front of the water bath. Here it's actually set currently at 50 degrees Celsius or 323 Kelvin, and we'll come back to why that's important a bit later on. So inside the water bath you can see we've got a beaker with some silver foil on top, and the foil is just there to stop the aspirin solution starting to evaporate. So in order to calculate the rate of aspirin hydrolysis, so over a period of time, we would quite simply just remove a sample from the beaker, and we would add that sample to a UV cuvette. You can see here now in the picture we've got our sample in the cuvette, and we would just do the UV reading. And remember, we'd be doing the reading at around about 300 nanometers, because we know at that wavelength salicylic acid absorbs UV light and aspirin doesn't absorb any at all. So we're monitoring the formation of salicylic acid, and the aspirin isn't going to interfere with that at all. So we've got a 50-degree water bath here. We could use, and we would use, higher temperatures, but if we do get too high with the temperature, then that might potentially change the breakdown mechanism. So the data we use to try and work out ultimately our expiry date wouldn't be reliable. So as we start to take samples from the aspirin solution in that water bath, what we're going to see is that the salicylic acid slowly starts to be formed, and the absorbance reading for each sample is going to start to rise. So you might get a plot which looks something like this. So the black crosses on this graph indicating the absorbance value after a particular time after which the sample is taken. So of course, remember, at the moment we don't really have proper units for the concentration of salicylic acid that we're detecting. We just have these arbitrary units from the UV spectrophotometer. So in order to convert those arbitrary units to a molar concentration, we need to use our calibration curve, which we learnt a little bit about in tutorial 2. So remember, when you've got the calibration curve or calibration plot, you would quite simply read across from the absorbance, read down, and that will tell you the concentration of salicylic acid in your unknown sample. Now, as I said earlier in the tutorial 2, we wouldn't probably actually draw the graph and read across like this. You would use something like Microsoft Excel to actually draw the plot for you, work out the equation of the straight line, then you would just use the equation of that straight line to work out the concentration. But essentially then what you would see is a plot, and note we've changed now the title of the y-axis. So now we've got the salicylic acid concentration, and here it's in micromoles per litre. And when you actually plot the values on there, the shape of the curve will actually be the same as the shape when it was just arbitrary units. So we've seen the salicylic acid concentration rising, and of course as salicylic acid is formed, the amount of aspirin present is going to fall. So the amount it falls by is very much related to the equation that we've got here and the stoichiometry of it. So that's the term we use, is referring to the number of moles essentially when something's reacting. So you've basically got 1 mole of aspirin reacting with 1 mole of water, and that will break down to 1 mole of salicylic acid and 1 mole of ethanoic acid. So as long as you have the molar concentration of salicylic acid, and we've just worked out how to do that already, then by subtraction you can work out what the molar concentration of aspirin is. So the plot will look something like this here. So it's almost, well it is, it's a mirror image of the graph that we saw with the formation of the salicylic acid. Now what I've done here now, I've tried to draw a line of best fit between these points, and you can see basically that we have a curve clearly. The straight line does not fit easily between these points. So because we don't get a straight line when we look at the aspirin concentration declining, that tells us something specific about this reaction. If we had a straight line, then it would say that the order of this reaction is 0 order. But clearly we haven't got a straight line, so that means this is not a 0 order reaction. So the next step that we try is something called a first order plot. So having seen that the hydrolysis of aspirin is not a 0 order reaction, the next plot that we try is the first order plot. So here we still have time on the x-axis, but now on the y-axis, instead of just having aspirin concentration, we've now taken the natural log of the aspirin concentration. So that's the ln button on your calculator. But if we were just using something like Microsoft Excel or Google Sheets, then we could just do this automatically. And when you take the data on that previous plot and take the natural log, you see that the shape of the graph changes considerably. So it's now moved from a curve to what is a very straight line here. So that straight line tells you that the hydrolytic breakdown of aspirin must be a first order reaction. And also what the line tells you is the rate constant for the reaction. So in order to find out that, we need to take the gradient of that line. So remember, to find the gradient we just pick 2 points on that line, ideally quite a long way from each other to be more accurate. Then you just look at the difference in the y coordinates of those 2 points, and you divide that by the difference in the x coordinates of those same 2 points. and that answer will be the gradient. And here the gradient will be equal to negative k. So k is the first order rate constant for the reaction. Now it's sometimes a little bit tricky here, and people do tend to make mistakes when they're looking at this. So of course, because that red line is going down, we're actually going to get a gradient which is negative. So if the gradient equals negative k, then what that tells you is k is actually going to be a positive value. So k will be constant under a given set of conditions, for example temperature, pressure, pH. So if we were to look at aspirin hydrolysis at a different temperature, so a higher temperature perhaps, then that rate constant would change.